If your ranker learns the wrong objective, better labels will not save it. I will show when Pointwise, Pairwise, and Listwise LTR work, and implement each with LightGBM in Python. This is the pattern you'll be able to implement by the end, which learns from rated labels and returns ranked results with an evaluation score. I'm Professor Pi, teaching search and IR with simple Python. Search and recommendation systems need to order results so users find the best item near the top. Learning to rank is the family of techniques that trains models to produce those orders from labeled data. Practitioners reach for Pointwise, Pairwise, or Listwise variants when raw signals alone do not give the ranking quality they need. LightGBM is a practical choice because it implements all three styles and scales to realistic data without rebuilding the whole pipeline. At a high level, Pointwise treats each document independently. Pairwise trains on swaps between pairs, and Listwise looks at whole result lists at once. Imagine two queries, each with 3 documents and labels like 0, 1, and 2. A Pointwise model predicts those labels. A Pairwise model learns which of 2 documents should come first. A Listwise model optimizes the quality of the top of the list directly. Each has trade-offs in data needs and what they actually optimize for. We will build a tiny toy flow you can run quickly. We start with a naive baseline, then train a Pointwise regressor, a Pairwise LambdaRank model, and a Listwise XeNDCG model. Finally, we'll show how to re-rank a small candidate set to see real gains in a simulated top 3 evaluation. Now we'll construct the tiny dataset and baseline. This snippet builds a tiny query document set and computes a baseline NDCG at 3 from a naive score. The lists X, Y, and Q encode 2 queries with 2 features per document, integer relevance labels, and query IDs. The variable S uses only the first feature as a Pointwise score, mimicking a simple BM25-like signal. The code selects the second query's documents, sorts them by S, and computes DCG with standard log discounts. To normalize, it uses the pre-computed ideal DCG for this query, so the result is in the range 0 to 1. If you raised K to 5 here, you would need a longer discount list and a new ideal DCG. The printed value summarizes top 3 quality from a trivial baseline. Next, we will train a Pointwise regressor and measure numeric accuracy. This snippet trains a Pointwise LightGBM regressor and reports RMSE on a held-out query. It first converts X and Y to NumPy arrays for LightGBM, then selects the training indices M for the first query. The model reg is a LightGBM regressor that learns to predict absolute relevance values with mean squared error. After fit, the code predicts PR on the second query's documents and computes RMSE, which is the root mean square error that summarizes how far predictions are from true labels on average. Increasing N estimators can reduce bias, but may overfit on this tiny data. Decreasing it regularizes and may raise error. The printed RMSE reflects how well Pointwise regression hits labels, not necessarily the ranking order that matters at top positions. Now, we will train a Pairwise ranker that optimizes swaps. This example fits a Pairwise LambdaRank model in LightGBM and tracks NDCG at 3 on the eval set. The lists GTR and GTE provide query group sizes, so LightGBM can form document pairs within each query. The ranker uses objective LambdaRank to optimize pairwise swaps toward higher NDCG, and the fit call passes eval set plus eval group to compute metrics on the held out query. The eval at argument requests a top 3 focus, and the model stores per iteration values in eval's result. Increasing N estimators generally smooths learning and can raise NDCG. But too many trees may overfit even on this toy split. The printed NDCG at 3 indicates how well pairwise training orders the top results compared with the baseline. Next, we will run a Listwise objective that treats lists as a unit. This code trains a Listwise XeNDCG LightGBM ranker with custom label gains and monitors NDCG at 3. The LightGBM ranker uses objective rank XeNDCG, a listwise loss that directly optimizes a cross-entropy over NDCG. The label gain array maps raw labels to graded gains, here amplifying gaps between high and low relevance, so the model prioritizes the very top. The fit call mirrors the prior step, supplying group and eval group along with eval at set to 3 and eval metric set to NDCG for consistent evaluation. Larger gains on top labels intensify focus on head results, while smaller gaps make optimization more forgiving. The printed NDCG at 3 shows Listwise training's top 3 effectiveness under the chosen gains. Now we will re-rank the baseline candidates with the best model. This code re-ranks the naive baseline's top 3 with the best performing LightGBM model to simulate a 2-stage pass. It first forms a candidate pool by sorting the second query with the simple first feature score. The trained Listwise model then scores those candidates with predict, and the code reorders them by the model's scores. It computes NDCG at 3 using a compact DCG calculation and the same ideal DCG constant for normalization. So the result is comparable to earlier numbers. Increasing K expands the re-rank pool, trading a bit more compute for potential gains. The printed NDCG at 3 reflects the end-to-end impact of model-based re-ranking over a lightweight candidate generator. To map this toy to production, think candidate generation as a fast first stage, and the learned ranker as a slower second stage that only scores a handful of items per query. The same approach scales by replacing the candidate generator with ANN, or a retrieval index, and by training on many more queries. Recap: Pointwise predicts labels directly and is simple, but might miss relative ordering. Pairwise focuses on pair swaps and often improves top ranking at modest complexity. Listwise optimizes the list objective directly and usually gives the best top-of-list quality, but can need careful gains tuning. Next step: rerun the Listwise experiment while tuning the label gains to intensify or soften focus on the top items and measure NDCG at 3 changes. If short, practical IR helps, subscribe and watch the IR videos.